The Rust programming language may be the best choice for your next embedded design. Then again, maybe it's not. Here are the reasons, then you can make your own informed decision as we speak to Jonathan Pallant of Ferris Systems on this episode of DevTalk with Rich and Vin. And here we are with yet another episode of DevTalk with Rich and Vin. I'm Rich Nass with Embedded Computing Design. The other guy at the other end, who is quite formally dressed today, is Vin D'Agostino,
Hey, Rich,
embedded systems developer. How's it going, Vin?
Great. How are you?
I've actually been better, but I won't bore you with my problems. But why the formal outfit?
I'm actually on campus at Stevens Institute, which is my alma mater right down the road from yours, and working with some students. And you won't believe, but I'm actually meeting a tailor today, and I thought I would dress up for the tailor.
So you dressed up for the tailor, but not for the students?
Well, I've dressed up for the students. Actually, the senior design professor, his class is meeting today, and I know him, and he said, "Oh, you're on campus. I want you to talk to my class." So I have to go in and talk. So I figured I would throw the jacket and tie on, and I'd see my tailor, and I would be a little more formal when I'm standing up in front of 40 students telling them what the world is going to be like when they get out.
Is the tailor going to talk to the students too?
The tailor will not talk to the students, and I suspect, although they get paid a lot more than you and I did when we graduated, that it'll be a while before they can afford custom tailored suits. So.
That's for sure. That's for sure. So the fact that you're there and you're speaking to students, and I know you're doing a little bit of teaching, that's a good segue into what I want to talk to you about.
Okay.
Rust. Are you familiar with Rust?
I assume you mean the programming language and not the stuff that appears on top of steel when it's left unprotected.
Well, it's actually, okay, let's go back to my problem. I got it in my shoulder, and I've been going to physical therapy because I got this rust in my shoulder. But anyway, let's not go there. Yes, I'm referring to the language Rust.
I'm familiar with it, but I have not done any major projects with it. I wouldn't call myself conversant. I know some stats about it because I talk about different programming languages when I'm teaching embedded systems, because they are much more resource constrained than if you're designing for the desktop or a server or cloud application. And so we talk about what it means. Everyone wants to program their micro in Python. I'm like, oh, okay, well, that's 78 times the amount of energy, and it's 30 times the size, and it's however much more execution time. So let's talk about what it means to pick a language or pick a peripheral or even pick a data structure and have that affect the size and running speed of your code. I think I've said this before on the podcast, but the first day of class, I say, look, the difference between a software engineer and a firmware engineer is that software engineers assume they have infinite resources, and we are way smarter than that. So, and that's how we start. So that's essentially everything I know about Rust.
Well, I sort of bring it up because it was introduced to me a few years ago, and it sort of got a lot of hype, and then it went away, and then got some more hype, and then it went away. And then at Embedded World not too long ago, there was a fairly sizable amount of interest in it. I saw a bunch of people, so I said, okay, I should probably learn more about this because I think this is here to stay. So with that, I said, okay, let's find myself a Rust expert who we could bring onto the podcast. And I found Jonathan Pallant. Did I say that right, Jonathan?
It'll do for me.
Okay, it'll do for you. And he's a senior engineer at Ferris Systems. So how are you today, Jonathan?
I'm doing great. Great to be here.
Good. So do you qualify as my Rust expert?
I'm happy to give it a go. No one's been doing Rust for 2 decades because it's not been around that long, but I've been at it for about 8 years now. So yeah, let's see if I can answer your questions.
Okay, so the first question, why are we seeing this resurgence? I mean, it hasn't been around that long, but I was going around Embedded World, as I said a month ago, and people wanted to talk about it. Why? What's going on? Something new?
I think there's a couple of things that are going on. So from my point of view, Rust never went away. There's been a bunch of us engineers both writing firmware in Rust and taking part in the Rust project itself, kind of working on the tool chain and things. I think recently announcements we've heard from the US government have kind of helped. So the former administration was saying, you need to take software reliability and security seriously. It's a big issue when people keep hacking these embedded systems. If you want to make everything an embedded system, you want to put wireless connectivity and all the things, you're going to have to start doing it properly. And we're going to start effectively judging you if you use a language that's not considered memory safe. And by that, we mean, is the language intrinsically going to help you avoid memory issues like buffer overflows? Is it going to help you with thread safety and avoiding data races and those kind of classic issues? And Rust has this kind of unique position of being a memory safe language, but it's also a systems programming language. So it compiles into machine code, and it can be the very first code your toaster, your microwave executes on startup. And that's not the case with Java or Python or C#, which are also memory safe, but they need kind of this this runtime underneath them. So I think, yeah, people starting to take security on embedded devices seriously is one reason for the uptick in Rust. And the other is, I think there's been some major moves forwards in the qualification of Rust tools. So before there was just the open source Rust compiler, but now we've got a selection of commercial alternatives that come with qualification for use in safety critical use cases. And that's made people start to think, oh, actually, yeah, maybe if Rust can do that, maybe Rust can work for me as well.
So go back to that runtime underneath them. What exactly do you mean by that? And what is that runtime that you're running underneath them?
So if you want to execute code written in MicroPython on a microcontroller, that Python code doesn't execute in your processor. Your processor only understands ARM machine code or MIPS machine code or whatever it happens to be. And that Python code is kind of translated at runtime. And that is the Python virtual machine that's executing that code. And that's providing a bunch of services, the garbage collection, heap allocation, and all those kinds of things. Whereas when you write C code, you put the C code into your C compiler, and it produces machine code that comes out. And there's nothing else required. It's like it's all there within the machine code, and that's enough to run the system. And that's where Rust plays. You can compile Rust code, you get machine code out. There's no runtime, there's no garbage collector, nothing else is required. That machine code is enough to get the machine running.
Interesting. Okay. Okay, I'll keep going. I thought you had a question there, Vin.
Oh, sorry, my audio kicked out for a minute. I actually do have a question. So one could argue that if you have a consistent support runtime environment for a language and it is secure and safe and certified, that any, let's say, scripting code you might write that runs on it, there's a group of people that I know in California who are trying to get everyone to write embedded systems in JavaScript. And they actually have a compiler, so it's not running an interpreted version of JavaScript. You write your script, you compile it down, it brings in the libraries that it says it has already checked and verified and everything. So let's assume that all those ducks are in a row. What makes a language like C or Rust different than those languages once they are compiled and running?
I think the major difference comes down to resource usage. I think if you look at history, people have gone to languages like C because they were able to get the job done using fewer kilobytes of memory and fewer clock cycles, which ultimately comes down to, fewer joules out of your battery. And if you can save, you need less RAM, you need a smaller battery, you can buy a cheaper processor from your silicon vendor's seemingly infinite catalog of parts. You save dollars on the BOM, and that's many dollars on the ticket price. And that just makes sense. So in these embedded systems, they're so often resource constrained and cost constrained. And sometimes you're not, right? Sometimes you're building 3 of them and they're going on a bench. And in which case, sure, go ahead, use MicroPython, use JavaScript. If that's what gets the job done within the envelope that you've got available, then that's a great choice. But very often, I've been an embedded systems developer for 20 years, built Bluetooth headsets and satellite modems, and we always had a very fixed set of constraints, and we needed to get an awful lot of compute done within that. And in the past, I'd have gone for C, and now I can go for Rust instead and be a lot more productive.
Well, you're right. People, something that people don't think about a lot is the implications of the things you learn when you take, let's say, a data structures and algorithms class, and you understand that the way you pick your data structure affects the kind of algorithm you could write, and the speed and size and reliability and even manageability long term of the code that you've written. And if you pick the right data structure, your code can become much simpler. And that sort of leads me to, are these languages inherently slower and larger in size because of these runtimes that could be compiled and running just as quickly? Or is it the construct of the language where you're trying to make it easier for a programmer? So, I mean, some of these languages, you don't even have to type your variables. Like every variable is exactly the same. And so you don't have to worry about, is it an unsigned character? Is it an unsigned 16-bit? Is it 32 bits? Is it a float? Is it a single or double precision with the float? Whereas a language like C, where you're typing everything, you are able to control how many resources are used for this one temporary variable that's going to exist for a very short period of time, right? I mean, that's a significant difference between some languages when you look at the difference between C, C++, C#, Python, even looking at older languages like Pascal, COBOL, all of those, right? So,
yeah, for me, it's about layers of abstraction. The more kind of layers of abstraction we've got to work with, the bigger the giants whose shoulders we're standing on, the less work we have to do as developers, but the bigger price we're paying. And in any kind of firmware project, I would say actually that's a piece of systems engineering, because the firmware doesn't stand alone. It's got to run on hardware and be a product that's got to retail in the market. And yeah, you've got to pick like an appropriate level of abstraction. And I think that's where Rust is really interesting, because previously it was, you can have the nice things, JavaScript, Python, C#, what have you, but it's going to cost you in performance, or you can have all of the performance and you're going to be sweating in the coal mines of debugging hell for weeks on end because a weird thing happened and everything crashed and you've got no real idea why. Where Rust has been able to move the needle is say, we'll give you all the performance of a C program. And all the evidence says Rust programs are about the same speed as a C program. I've seen some run 10% faster even, but we say broadly the same. So you have all the performance, but you can have all the productivity at the same time. You can have a standard library with nice data structures. You can have a compiler that's on your side that actually goes, hey, you've made a mistake. Line 5 doesn't work with line 7. I'm going to literally underline them in red and point a big arrow and say, yeah, you need to rethink about line 5. It doesn't work for these reasons. Here's a link. You can go and, read more stuff online, as opposed to, the C programming language comes from a time when you were lucky if the compiler said syntax error. It's a language designed for doing compile jobs overnight on punch cards. So Rust was able to give you the performance, but give you the kind of the productivity and the safety at the same time.
I would agree, but I would challenge you that's not necessarily a construct of the language, but a construct of the tools and the philosophy of building the tools for working with the language. There's nothing inherent in the language itself, because the language is just, as you said, compiling down to, opcodes or machine language instructions. And at that point, I mean, you could write safe and structured assembly language, but the language doesn't lend itself to that. I talk to my students all the time because, and people always say, well, I'm not going to use C, for example, and this is maybe a discussion 10 years ago, because I can write it smaller and faster in assembly. And I say, you know what? There was a time when that was true, but it's not anymore. because the tools have gotten so good that the compiler and the optimizer will find parallelism in your code that even if you saw it, you wouldn't write your assembly that way because it would be unmaintainable. But at a high level, you can write it the way it's maintainable and it makes sense. And you can go back 3 years from now and say, oh, that's what I was trying to achieve here. And yet the tools can make it more efficient by finding this parallelism, reuse of code, a jump instead of a return because it knows it's doing something else because it's looking ahead. So I think you can't look at a language anymore by itself. You have to look at the environment for developing it as well, or
Yeah, I think
developing
that
with it.
I think that's fair. I can give one example of where the tooling and the language kind of co-evolved. So again, looking at Rust, we have the idea of pointers in Rust, but we prefer the idea of references. And references are tagged with the notion of what are you pointing at and how long does that live for? And that kind of applies in C, but the human has to hold that kind of knowledge in their head. In the Rust language, there's actually a mechanism built into the language to say, I've got a function, it's going to take a reference, it's going to return a reference, but actually these two are associated. That thing I'm giving you back is actually just completely associated with the first argument you gave me, and you need to tie those two lifetimes together. Or maybe it's the second argument, or maybe actually the returned reference comes from somewhere else in the program. But when you don't have a language syntax to be able to express that, that then massively limits what the tools are able to do. People write static analysis tools in C, and they have to do a lot of hard work to kind of understand the program. Whereas when the language has been designed to allow for that kind of analysis, then it can be done a lot more easy, and it just sort of becomes a natural part of the ecosystem.
Yeah, I mean, a good example of that is null pointers, right? You pass a null pointer, that's a classic job interview question. So anybody out there listening who's about to go on a job interview, most people will say, write me an algorithm that takes, or write me a function that takes this and this, and the argument is a pointer. And if they don't test for a null pointer at the beginning of the function to make sure that the pointer is valid, then they immediately lose some credibility in the interview, right? Because there's always a possibility that a null pointer, gets sent for some reason. So I totally understand that. But now the question or the discussion is, are we better off making safer languages or putting that effort into training engineers better?
I think we can point to kind of history and say, if it was possible to educate engineers that they could just write perfect software, I feel like we'd have done it, because some of the mistakes they made are expensive. And I think there's also, I like to think engineers have a certain computational budget, right? There's a certain amount of brain power you can give to your job. And history has shown that if you can take some of that work away and teach the machine to do it, the humans use that spare brain power to build better and more interesting things, get their work done faster. And I think we can see with Rust that when we've taught the compiler to manage which items borrow from which other items and how long everything's living, and does this system even make sense, or is it kind of nonsensical because you've ended up with dangling references? By not having to think about that as a human, I'm free to spend my brain power on kind of more interesting problems.
Very good.
Okay.
So what are some of the application spaces that we should expect to see more heavy use of Rust, and why?
It's really interesting, because it's something about firmware developers. They don't seem to love writing blogs about how they do their day job, right? All the hyperscaler companies got into this 5 or so years ago. The Amazons, the Microsofts, and the Googles of the world, their back end is kind of in Rust now, and they wrote about it, which is great. I know a number of people are doing Rust in firmware on embedded microcontrollers. They don't love to talk about it. Sometimes I feel like they've discovered some kind of secret hack to making better firmware faster. But I can point to a couple of examples. Microsoft have a security processor called Pluton. It's one of the security thing. Firmware is written in Rust. So if you've got a Pluton chip, I'm pretty sure the shipping ones are running firmware written in Rust. Google have the same thing. They have a security processor in Chromebooks. It's written in Rust. If you go out today and buy certain models of Volvo and Polestar. I want to say it's the Volvo EX90 and the Polestar 2. Other brands of vehicle are available. The cars shipping off the production line today, the low power management system is written in Rust. They had that done years ago, and that's shipping today. And I think you're going to see a lot more interest in the automotive space. I can't talk about who my customers are, but trust me, there's an awful lot of interest in that space, especially now qualified tool chains are available. I know a company is doing a 3D ultrasonic sensor. It's like a module you can fit to a robot to kind of tell you where you are in 3D space using basically the audio version of LiDAR. They're doing all the firmware in Rust, and they're going for SIL 2 certification. So that's going to be a really early example of Rust firmware actually used in a safety critical system. So I think there's going to be a lot more. I know there's a lot of projects that have started and are on the way, but those are some of the ones that I know are kind of further down the line.
Well, you're highlighting actually what I would call an inertia-based barrier to entry on this, which is if Microsoft were to support Rust in Visual Studio, you would start seeing a lot of desktop apps being written in Rust because it's there. And certainly for Windows-based programs, Visual Studio is probably the #1 environment in which people write their programs, right? On the micro level, every MCU manufacturer has their own set of tools, right? There's MPLab X for Microchip. There's eSquare Studio for Renesys. There's SPM32 IDE or Cube IDE for ST. And so, and then that doesn't include all the private people like Sager and IAR and stuff who are supporting the industry. So you would have to get every one of those companies to say, we're going to support not just LLVM on C and GCC for C, but we're going to support Rust as well. And for them, the lift is that every code example they write to support a peripheral that's on the chip, they now have to have, multiple versions of these examples in order to understand how to use the peripheral in each of these languages. So how would the Rust community start to make that happen?
Yeah, it's a really interesting one. I describe these kind of I describe these as islands, right? You're either on kind of Nordic island or TI island or ST island, and it's quite hard to sail from one island to the other. We saw that was a problem during the chip shortage, right? You're stranded on one particular island, you run out of chips. It's kind of hard to switch over. So a lot of the community work that's gone into the Rust embedded ecosystem is all around building abstractions where we don't actually care so much which chip you've got. We've got a standard interface, we call it a trait, that describes, for example, an SPI controller. And if you want to take your little LCD screen, it's written against that abstract trait. And so it doesn't actually care whether that driver is running on a chip from ST or a chip from Nordic, as long as the traits have been implemented, we would say in the lingo, for that particular device you're using. Now, currently, not a lot of silicon vendors doing that. That is something I do keep talking to silicon vendors about, maybe see a little bit of movement. I want to give a shout out to Espressive, the people who make the little ESP32 Wi-Fi chips. They loved what was going on in the open source community on their chips in Rust. So they basically hired them all. So Espressive now has a Rust team, and there is first-class support from them for Rust on their microcontrollers. We've also heard noises from Infineon supporting Rust on some of their automotive parts. And we saw a press release a couple of months ago from ST saying they were interested in Rust on some of their automotive parts. The other thing I would say is I've built embedded systems in the past where, frankly, I won't say which silicon vendor, but I looked at the silicon vendor stack and I gently swept it all into the bin. And then I wrote something bespoke for the application we were doing, because we were super critical on the resources we needed. And so actually you don't need to use the silicon vendor stack. We've got the information. You can just build it yourself, and if you're going to do that, you could do it in Rust as easily as you could do it in C. Again, it's trade-offs. Maybe resource usage is less critical. You'd love the leg up the silicon manufacturer is going to give you, and I would love to see more silicon vendors offering first-class Rust support. But in the meantime, the open source community, I think, is backfilling that admirably.
Cool.
So one last question from me. What language is it supplanting?
I get all kinds of people in my trainings, right? I get the diehard C developers who are being told or want to switch over to Rust, but I get Python and JavaScript people in my trainings who are like, yeah, we want to learn Rust because we'd like to keep all of the nice things. We'd love to have a language, with built-in dictionaries and lists, but we need the performance. So actually, I think it's starting in the middle, and I think it's coming for everyone.
Very good.
Okay. I have one last question, because you
Shoot.
did talk about performance, and especially on the embedded side, clock cycles and memory are really important. And and it's been a while since I've looked at these stats, but there are people who compare programming languages. And you had said, and I agree, and the data supports that, from execution time and even from an energy usage time, Rust is pretty close to C. If you consider C, the base, so 1.0, Rust is 1.03 in energy usage and 1.04 in execution time, comparing it to Python, which is 75.88 in use of energy. And you wonder why all these AI searches take so much energy. And 71.9, so almost 72 times the amount of time to run the same algorithm. When you look at code size, however, if the smallest is Pascal, but nobody wants to write in Pascal anymore. C is about 1.2 times that. So again, not too far. But Rust is 1.5.
I see you've done your homework here, Vin.
Yeah. But this happens to be a slide that I use in class when we're talking about how green is your language.
Okay.
Now, this data is a few years old. So and people will find this data. So I want to bring it to light, because someone's going to say, well, okay, you talked about the two good things, you didn't talk about the bad thing. What advances have been made over the last 2 or 3 years on code size? Because at the publishing of this table, the code size for Rust was about 1.5 times the size of C. So, but compilers, tools evolve all the time. So tell us where it is now. And as you said, relatively young. So
yeah, so that's fair. Some of this comes from Rust's standard library. Actually, Rust has 3 standard libraries wearing a trench coat. The top one is the thing that cares what operating system you're on. It does file systems, threads, and networking. The middle one has the heap allocator, and the bottom one is what we call libcore, and that's just your basic Unicode string handling, your basic data types like result and option for declaring, errors of whether things have been found or not. Now, that has all been developed, I think it's fair to say, with a primary focus on desktop applications, and they were super keen on performance, and they were relatively relaxed on choices that affected the code size, because it's a big desktop machine. That wasn't the primary focus. That focus is changing, but the problem you've got is you kind of need to pick one. Right? You've either got to choose whether you want to optimize your standard library for performance, or if you want to optimize it for code size, because these are in tension. So sure. 2 things. One, the Rust project are looking at ways they can allow you to make those kind of choices when it comes to using the core library. In particular, our version of printf tends to produce quite large code. It's quite good performance, but it does chew up quite a bit of code space. That is fair. And the examples, the numbers you get will kind of depend on how much sort of string formatting and printf style stuff you're doing. The other thing is, my company, Ferris Systems, we've developed a logging mechanism. It's an open source project. It's called DFormat, stands for deferred formatting. And what we do is we take your log messages and the arguments you want formatted within them, and we don't put the log string on the microcontroller. We put it into the debug section, and we replace it with a very simple integer. And then when it comes to logging, your log message says, please send log message number 5. The first argument is 6, and the second argument is Y. And the laptop then receives that, and that's only like 5 or 6 bytes of information. The laptop looks at the debug section of your ELF file and goes, you're printing log message number 6. All the string formatting happens on your laptop, where you've got all the time in the world to do it. So there's kind of one way to bypass the problem. You go, string formatting is kind of expensive in Rust. let's simply not do any string formatting and move the problem elsewhere. And I've seen simple programs drop from like 60K to 5K just by taking out, in particular, floating point formatting is quite expensive. So yeah, people are aware of the issue, and there are some nice solutions to it.
Right. And I should also say for our listeners that those numbers I was giving, and because that's how they did these tables, was assuming a bare metal design. But if you are adding an RTOS or anything else to that, the size of the code grows automatically from that. And the stuff that is in Rust is essentially thread safe from the beginning when you're writing it. And so if you're going to work with an OS, in C, you have to adjust those numbers in your thinking process when you're trying to compare it with Rust. So for those who are listening, that's an important thing to know about.
Very good. Well, thank you very much, Jonathan. I know I learned a lot here.
Yeah, my pleasure. It's been great fun. Thank you for having me.
Yeah, thanks for joining us.
That was Jonathan Palin. He's a senior engineer with Ferris Systems. So what do you think, Vin? Is this thing gonna take off or what?
It's an interesting place to work. I think they have the same uphill battle that RISC-V has, in that the installed base and the thinking process is going one way, or they're trying to change it. And it's very much an ecosystem-based move. I mean, that's how ARM got and C got their stranglehold on where they are. So they took a bunch of stuff that was everywhere. Everybody had their own architecture, their own whatever, or their own assembly language, and they centralized it into a language that could run anywhere, and centralized it in in an architecture that everybody could use. And that's why everybody's proprietary ones kind of went away. And now we're dealing with a shift on the hardware side to RISC-V, and on the language side, we're looking at something like Rust that is challenging C, which is obviously the,
Uh-oh, I think we lost you, Vin. So I think we're gonna cut it off right there. So thanks everybody for listening, and we will see you on the next episode of Dev Talk with Rich and Vin.